Hi, this talk is about leveraging learning-based techniques to improve control concurrency testing. I'm Suvam from Microsoft Research India, and this is joint work with Pantazis, Arpita, and Akash. Consider this concurrent program. There is a shared variable called value. The main function creates a couple of threads, T1 and T2. The first thread goes to sleep for a while and writes 3 to value. The second thread goes to sleep for the same duration and writes 5 to value. The sleeps are introduced just to put in deliberate context switch points. The main thread waits for both of these created threads to finish and finally asserts that the value is 5. Our task is to find an execution of this program which violates this assertion. The high-level architecture of control concurrency testing is as follows. There is a concurrent program which is under test, and there is a scheduler which serializes the execution of this concurrent program by making control decisions. So the scheduler can observe the next state of the program along with a bunch of enabled operations. So in this case, the enabled operations might be the two sleep operations, which is represented here as O3 and O5. The scheduler uses some strategy, which we represent here as a black box, to choose which is the next operation to execute. So in this case, the scheduler might decide to execute O3, and for testing purposes, the sleep is just a context switch point, which we choose to take or not take. The next operation might be O5, and then the scheduler might decide to do the write in thread 2. This might be followed by the write in thread 1, and finally the main thread executes the assertion, which now fails. The failure of the assertion happens because the write of thread 2 preceded the write of thread 1. You now get a reproducible buggy trace which tells you all the operations that if you execute in this sequence will result in the assertion failing. The space of control concurrency testing can be partitioned into two groups, algorithms which are stateful and those which are stateless. Stateful algorithms are exhaustive, but they require a full program state representation, and this is often hard to do in realistic programming languages. Stateless algorithms such as random and probabilistic concurrency testing have been known to be effective on real-world programs. So these depend on heuristics to choose the next operation based on empirical observation of bug patterns. So these observations might be that bugs occur with few context switches and few ordering constraints and few deviations from a deterministic scheduler. And the idea is that these heuristics focus the search on interesting subspaces of the entire set of program behaviors. But what happens if your bug does not conform to one of these known patterns? So what we observe is that all of these algorithms regress in their bug finding ability. And the reason is that these algorithms do not actually learn while they are doing the exploration, and they're applying the same heuristic to every program under test. Our contributions are as follows. We devise a systematic exploration strategy based on Q-learning. Our focus is on doing well on coverage, and we strike a balance between exploration, which is to randomly choose the next action, and exploitation, where we adapt our choices based on decisions that we've taken in previous iterations. This allows us to have a search strategy which is highly customizable, and it actually adapts to the program under test. We've implemented this in C#, evaluated on micro benchmarks, and also production services from Azure. At a very high level, this is what the learning-based control concurrency testing architecture looks like. You still have the concurrent program under test, and we now have a scheduler which is based on Q-learning, which we leave as a black box for now. We observe the next abstract state of the program under test, and I'll discuss what abstractions we use very soon. We still observe the set of enabled operations from this abstract state, and we also observe a reward signal from the program under test. And we pick the next action based on a softmax policy. So to draw a comparison with reinforcement learning, you can think about the scheduler as being an agent which is trying to explore an environment which is the program under test, about which it has no prior information, right? So every time it's picking an action, In response, the environment or the program under test is informing the agent about the next state along with a reward. And the job of the scheduler is to maximize the expected reward. This whole strategy optimizes for coverage. Bug finding is actually a weak signal because once you find the bug, you just stop there. So instead, we try to do as good as possible on the coverage metric, and the bug finding ability comes as a byproduct. This also allows the scheduler to be highly resilient to different kinds of bug patterns. And we are not just about resolving control non-determinism. We can actually also handle non-determinism in data. So if we have a construct like if star execute S1, otherwise execute S2, we can actually figure out what is the value for this star operator, which allows us to maximize the coverage. So we learned that as well. So prior algorithms like random and PCT resorted to pure random resolution. Therefore, if you have data non-determinism, they can't do any better than random. Whereas we can do much better because we're learning what is the best value for this star operator. I'd like to highlight the point on coverage optimization using this simple calculator example. This is a message passing program. You have a calculator which is internally maintaining a counter, and it's receiving messages from different actors. So when it receives, for example, an add message from A, it will add 1 to the counter. If it receives a multiply message from M, it multiplies the counter by 2. If it receives a reset message, then the counter is reset to 0. And if it receives a divide, this is an integer division. And we also bound the value of the counter between minus 5,000 and 5,000. So there are 10,000 unique possible values of this calculator. So if we plot the number of uniquely visited counter values for the different scheduling algorithms, we find that QL almost observes all the 10,000 unique counter values, whereas PCT is the next best, observing only around 4,000 unique counter values. Why did this happen? So if you think carefully, you'll realize that from any state, reset is a bad action to take because you're just going to go back to a state which you've seen already, which is 0. Similarly, in terms of which is the next worst action to take, that would be divide because this is integer division and you're likely to go back to a state you've seen already. In these graphs, the x-axis denotes the number of program runs. The y-axis denotes the number of times an action was taken in a particular program run. We observe that QL very rapidly learns to avoid the reset action. In fact, it has also learned that divide is the next worst action to take. In contrast, random and PCT does not do any such learning. The distribution of actions remain almost uniform. Observe that the fact that reset is the worst action followed by divide is a fact which is very specific to this application, and QL learned it during its exploration. And this is the reason why it achieved superior coverage for this example. So the time has finally come to unbox the QL strategy. Recall that you can think about the scheduler as being an agent which is exploring an a priori unknown environment, which in our case is the program under test. So this program has some concrete state sigma, and what QL observes is some user-defined abstraction of it. In addition, for every state and operation, QL maintains a quality metric called the Q value. It uses these Q values to pick the next operation based on a softmax policy. Once it has picked an operation, the program executes it and informs QL about the next state, the set of enabled operations, along with a penalty. The reason we have a penalty is because we want to nudge QL from taking the same operation from this state again in the next time, right? We don't completely prohibit it, but we slightly reduce the probability of this operation being picked from this state the next time onwards. And the way it's done is using this value update rule. So it incorporates all of this information into this rule along with these additional parameters alpha and gamma. And the effect is it's updating these Q values for every state operation pair. QL brings about several interesting design considerations. The first one, of course, is the abstraction function. The design of this function presents a similar challenge as in standard abstract interpretation. With an appropriately defined abstraction function, you can make QL stateless, stateful, or anywhere in between. In our own experiments, we had several design choices. For actor-based systems, we could either choose to track just the inbox of in-flight unprocessed messages, or a default abstraction where we track the inbox along with the state of every actor or worker, or we could choose to have a completely user-defined custom abstraction. And the open question here is, what is the best abstraction function for a particular application? Likewise, there is design to be made in the reward function. We typically went with a standard negative penalty, but we also employed an optimization which increased this penalty with the frequency of the number of times we visited the source state. And this was just to accelerate the degree of learning. We also picked an optimization which assigned high negative rewards for specific actions such as failure injection and timeouts. And the objective here was to kind of delay injecting these actions early on because they prohibit exposing interesting program behaviors. And the open question again here is, for a given application, what is the best reward function? And as you saw in the value update rule, there are these parameters alpha and gamma. We experimented and went with a particular pair of values, but in general, it's an open question what these alpha and gamma parameters should be for a given application under test. Let's now look at another application. Raft is a consensus protocol where there are a bunch of nodes in one of these three roles. There is a leader which receives and replicates client requests. There is a follower which tracks requests received by a leader. And there are candidates which can start leader election processes. And the invariant that we want to maintain is that there can be at most one leader at any particular point of time. And there is an implementation of Raft in Akka which violates this invariant. And in order to increase the likelihood of exposing this bug, what you should do is, in any particular run of the program, you should try to maximize the total leaders elected, as well as have leader election rounds with multiple candidates. If you do these two, then the likelihood of hitting the bug increases. The graph on the left plots the total number of elected leaders as a function of program runs. And we find that QL with custom or default abstraction is able to explore a higher number of total elected leaders compared to other abstractions or other exploration strategies. The graph on the right plots the election rounds with multiple candidates as a function of program runs. And here again, we find that QL with custom or default abstraction is able to expose election rounds with more and more candidates compared to other abstractions or other exploration strategies like PCT and random. And these two taken together explain why QL with either the default or custom abstraction is able to find the invariant violation more effectively than other scheduling algorithms. So this slide highlights our experimental evaluation at a very high level. So we evaluated on a bunch of complex protocols, multi-threaded benchmarks from SVComp and SCT benchmark suits. SafeStack and bounded buffer are known to be extremely challenging benchmarks. We also evaluated on production services from Azure, which are currently servicing hundreds of thousands of VMs. And these have unit tests which check for functional correctness as well as fault tolerance. So our evaluation metric primarily was bugs 100. So we invoked the scheduler 100 times with a particular scheduling strategy, and we report the number of times that strategy was able to find the bug out of the 100 invocations. And we also report the geometric mean of this metric. The number in the subscript denotes the total number of applications where the scheduling strategy found a bug. And we observe that QL was able to find bugs in all 16 applications, and it also resulted in the highest bugs 100 metric. In summary, we presented a controlled concurrency testing algorithm based on Q-learning, which balances between taking random steps and informed decisions based on previous explorations. We integrated this into the P-sharp framework, and it outperforms state-of-the-art strategies on micro-benchmarks and production services from Azure. You can try our artifact out from this link, and at this point, we would be happy to take any questions. Thank you.